My name is Julia Scott. I'm in the bioengineering department at Santa Clara University. I'm trained as a neuroscientist with 20 or more years in neuroimaging experience and about 8 years of putting together biosensors with virtual reality. And the combination of those two things makes something magical when it comes to changing brain health and the way we think and feel. The primary applications I've built this in is in cognitive health for older adults and also mental health interventions for adolescents. With that work, it requires working across a lot of different domains. So kind of the set of affiliations I have here are the pieces of the puzzle of working with technologists in the immersive media space, thinking through the ethics of using these new technologies with youth and people with cognitive impairment. And that's the ethics work. And then commercializing what we've done. So I'm founder of Gambit Labs, which is building closed-loop games to train cognitive skills. Something we developed in the lab was licensed out and created a nonprofit called Content for Good, which is using VR as a medium for immersive storytelling for education and training. Our first products have been with dementia care training. Coming up, hopefully by fall, I'll be setting up the Health Technology Lab at California Institute for Stress and Resilience, which is just about 10-15 miles from here in Mill Valley. And the intent of this institute is to really take a precision medicine approach across multiple technologies, digital and biological and behavioral, to optimize health, especially in older adults. So today, with the short time I have, giving you an example of what my lab does and how we approach the design process, particularly on validation. So there's 3 verticals, one in neuromodulation, the second in the BCI for VR, and then in identifying neurobiomarkers for emergent properties, right? Things that have established and we need to establish in order to say something is really affecting the brain. If we are going to say technology for brain health, we need to measure the brain. Today, I'm going to focus on an example with neuromodulation, and that is the freshest data. You are getting data from last week. My student just submitted his thesis. Hallelujah, it is done, and so that's what you're seeing today. And I always look at this in three types of evidence that something is working. The engineering of the technology is one. That comes first before you put it anywhere near a person. Second, evidence via behavioral measures and physiological measures. And because if we don't have confirmation across all 3 of those domains, we don't really know what it is doing. Okay? And there are lots of ways this can fall into place that we need to understand. That engineering component of it is one piece of understanding the mechanism of how it works. The neural correlates or other physiological correlates are another way of saying, how does it work? We need to understand the mechanism. If we don't understand mechanism, we're stuck finding clinical outcome evidence over and over and over again, and you don't have something generalizable. Okay? A placebo. Your expectation on whether something will work or not. So sampling in a population that does not have a strong bias on whether something will work or not, or the expectation that a technology is good or bad, that is extremely important in how you design your studies. And then the last piece of this is individual variation. We are all unique in our physiology and in our brain networks. And so things will work for some people and not for others. And we need to know why. So we design technology for the group at hand. And the examples I have here are these 2 little devices, and these are little. One is the Motif Neurotech. It's 9 by 9 by 11 millimeters, and it sits in your skull. Their intent is to treat depression. The second one, this disc, is Inner Cosmos. Inner Cosmos' product, in that one, you slightly shave the skull, then you put the little wafer on there, and that stimulates the brain. Both of these are brain stimulators, both intended to treat depression. The companies are at the first engineering stage of validation, and they are being diligent about it because they're trying to treat something as difficult to measure outcomes for as depression. Okay, but this is the promise that neurotech has. And when I'm teaching my neural engineering class, these are the case studies that I use, amongst others. So it's not just the consumer stuff, it is the medical process as well. So the neuromodulation method I am looking at is photobiomodulation. This uses near-infrared light to change our physiology. This is well established in soft tissues. You can get a cell to produce more ATP. You can inhibit inflammatory molecules. You can even get amyloid plaques to clear from outside of the cell when you apply this energy directly. That's not a question. The question is, can you apply that energy at the surface of the head and actually reach the brain to have these effects? So it's a question of the human neuroscience, not the fundamental neuroscience. The systems on the market are in the wellness domain. They are not yet FDA cleared because they cannot measure the mechanism or evidence in humans yet. If we can, and we can demonstrate that we can design a device that safely emits near-infrared light to the brain, we have a safe, non-invasive approach to treating dementia, Parkinson's, traumatic brain injury. So it's something worth investigating. But to get to our first thing of the engineering, we need to have 100% knowns, as much, well, it's never 100%, but as much as we can. So we built a device from scratch, and that's what we see here. So all of the source properties are known. I can control every single light by string on that system across all the parameters. And so that's something I can manipulate and create experiments, which will give me the greatest amount of data. The other component of safety. This is relatively safe. Our biggest risk is heat and light. So those two things we have optimized, so we know it is safe to run on a person, and then to compare it to what is on the market, what's being produced in the factories and being sold, right? And so we're comparing it to the neuronic light as our comparator. So this is one component. So now that we got a functioning system, the control system works, we know it doesn't heat up too much, we know we're not hurting the eyes, we can move forward to our human experimentation. And the question here is, what is it modulating? Because as I mentioned, this type of energy affects not just one thing in us. Just like the sun affects many aspects of us. This is a spectrum of that light, kind of the equivalent of 4 hours in the sun. It will give you what this device will give you in terms of the spectrum of light. Okay? But our interest is, one of those is in cognitive health. So we're asking, does this have an impact, not just on the general physiology, but on neuronal excitability? In the animal models, it's demonstrated that a particular channel is responsive to light. So not just the eyes, but inside your brain is TRPV4. So those channels, when they receive this type of light, they open, more positive ions go in, they're more depolarized, more excitable, more cognitive function, so to speak. How are we going to measure this in a whole person? We need to look at cognition that modulates based on our state, where if we increase a particular wavelength or frequencies of brain activity, it should affect performance. So what we looked at simultaneously, sorry, ooh, that got distorted. Oh, that's not the right direction, sorry. Okay, what we looked at simultaneously is heart rate, which can be modulated by this by photobiomodulation, heart rate variability in particular, as a systemic effect. That's one component, non-neural. The second, looking with EEG and looking in the theta band, and the theta band, 4 to 8 hertz, is correlated with cognitive load. When you're thinking about a whole lot of stuff, right, trying to remember a lot of numbers, directions, and so on, theta power increases. This is reliable in normal cognition, the whole spectrum of cognition. So we paired that with tasks that are based on load, so working memory and processing speed. And then we had to pair our stimulation with a protocol that would increase theta, right? So if we're trying to increase theta so that performance on working memory and processing speed would increase, we need to have a 6 hertz pulsed stimulation frequency. And one of the principles of pulse stimulation, whether it be by visual stimuli, electrical stimuli, is that it causes an entrainment, which means the oscillations at that frequency will increase in amplitude. That's what we're calling neural entrainment. So our biomarker here is neural entrainment. Our systemic marker is HRV. Our behavioral outcome measure is working memory and processing speed scores. Okay, so I apologize for the distortions and the conversion to PowerPoint, but what you see here is our experimental design in a single session across 3 different conditions. First, or not in a randomized order, we have the 2 comparators, our prototype, the commercial device, and then the person experienced the sham with or without, or sorry, the sham with the prototype or with the commercial device. Right? And they took the cognitive test, we got our baseline readings, we did the stimulation, and then we did our readings, and then we did the cognitive test again. Right? So that in a real world setting where you're using the stimulation on a daily basis, in practice, people put this on in the morning, go on the rest of their day. Is there any measurable effect on cognitive performance after using the stimulation? Right? And our clinical protocol, the duration is what is similar to use. Okay. So preliminary findings. What we saw with that 10 minutes of stimulation, we did not see an acute change in performance on the cognitive task. So with this particular experiment, in that category of behavioral evidence, we have not checked that box. Right? Second, the neural signatures. We would expect to see 6 Hz neural entrainment. And from the group analysis, we are not yet seeing that. However, the way we have analyzed it is the mean over that entire period. I need to complete the time series analysis to see how it evolves. So we'll say this one is still open, inconclusive at this point. HRV as well did not change. So, but what we did see, the dominating factor on what variance in these measures was individual variation. So if your heart rate variability or your theta was, if your theta, in this case, if your theta is low, your potential change in theta was higher, right? So they're negatively associated with one another. And so coming back to those 3 principles I talked about, right? Does the thing work? What is the mechanism? And then what's the placebo effect and what's the individual variation? Right now, that individual variation is the strongest factor at play. What I do need to look at is different analytical methods and play around with that protocol. But one of my skepticisms of this modality is that it does not have the ability to reach the human brain. When that light goes through your tissues, the attenuation is over 99%. So if this is going to be a commercial technology being marketed to people with dementia, as this might help you, and you say there's animal models that show it can clear amyloid, that is true. But can you do that in the human? So having credible neurotech is really important. And with the last minutes I have, I want to incorporate what the direction of ethical use of neurotechnology is being guided by. And the UNESCO Working Group on Neurotech Ethics has put in their final recommendations that will be voted on in November. And looking to that, I read through all 158 articles of that to understand what the global norms will be on how we use neurotech. So number 1 is respecting autonomy. And the next is, all of that follows is how. How are you going to respect the autonomy of the person? And it's the full life cycle, including the research, consumer and medical, inclusive of the data inferences and multimodal aspects. So eye gaze in combination with this. If you are making inferences about what is going on in the brain, it's going to be covered by this, not just implants in the brain. Okay. So let's see what happens in November with those final recommendations. The other question for organizations, whether they be labs, companies, and so on, or medical system, is how are you going to make these good choices in the validation process, in the implementation? That's not easy. I just listened to Louis Rosenberg over on collective intelligence, how we make decisions as a group, right? These are hard things, and what helps is a process. So whatever the set of ethics or values are, how you implement them and the transparency is really what matters. And if one organization's set of ethics on how neurotechnology is used is to use that to augment the human and integrate with the internet, at least I know that, and I know how they came to their decisions, and I might not want to play. But that's fine. Others will have medical uses. And so I want to point you to a resource that was developed by the Vatican and my university. Odd place, you might think, but it is super useful because it is literally a process map of how to go about setting up your organization in that decision-making process. It is not just evangelizing Catholic values. It is the process of decision-making. And the book is called Ethics in the Age of Disruptive Technologies. So I'll leave you with those things, and to give thanks to all of the people involved in this. Here you see Mike and Karis running those studies. And Mike just graduated, looking for work. He's a really, really diligent electrical engineer. I have an extensive team of students. I work with the Ethics Center and with XRSI, which is a privacy and safety foundation or organization for emerging technologies. You can reach me at either of those two emails. Thank you for your attention.